split DFS problem and connected components we have to find. So we are just said that we have some stones on a x and y axis, suppose, and we have to make sure that we can remove all those stones which lie on the same x or y in the same row or else the same column. We can remove some stone if there is another stone in that row or column. So can I remove this one? Yes, I can, because I have something in the row or column. Can I remove this one after removing this one? Yes, I can, because I have this stone. Can I remove this one? Yes, I can, because I have this. Can I remove this? No, because I don't have anything else. So at last I'll be having 2 stones left. Can I remove this? No, because I don't have anything in that row or column. So 2 will be my answer. Now basically what we are doing is we are just basically calculating the number of connected components only, right, over here. That if this is a connected component and this is a connected component, then we can say that those many number of stones will be left at the end. So how many did we remove? We removed total number of stones minus the connected component number of stones equal to the removed, and they are telling us to find out largest possible number of stones that can be removed. We need to find out this removed part, so n minus connected components. The main part of this problem is making the graph. How do you make the graph efficiently? I did not explore much about this. The way that I saw in the tutorial and I followed was, for each of this one I'll just check for all the other stones, if there was, apart from this obviously, if there was some other stone, right, which lies in that same row or column. If it lies in the same row or column, I just make the edge from that to that row. So if there was some stone over here, right, I will make an edge from here to here also, and then from here to here also, and then from here to here also. Similarly, everything is connected, right, in that way. Basically what I'm trying to say, I will just check. I have a stones array, right? I have the stones array, and then in the stones array I will just check if the x coordinate of that I is equal to the stones of any other one. So suppose if I take one, what are my I and j's? Stones is just an array, a 1D array, suppose, not a 1D array exactly, but it will have stone 1, stone 2 coordinates, stone 3 coordinates, and far on. So I and j's are these two, in the sense 2 pointers depicting different stones at different points in time. Now if we see that if these two edges, right, have something in common, we'll make a node from this to this, we'll make an edge from this to this. If there is something common in the sense, if there is a row or a column common, we'll just make an edge from there to there. So this is how we'll make the graph based on indices of those stones. Here we are doing the same thing. We make the adjacency list to make our graph. We check for each pair if there is something common, either the edge row or is the edge column. If it is column is same, then we'll just push. This one part is like j is getting pushed as I, and then I is getting pushed as a j's neighbor. So it is a bidirectional graph, right? Undirected or bidirectional graph. So we can just do this, and then to make a DFS possible, we make a visited array basically, and then pass that visited into the. Over here also some more modifications we could have done. We could have made this visited array as a global variable. We did not even need to pass visited over here then as a global if we would have made. And then we just run a simple DFS, mark something as true if that node is in picture and we are trying to explore its children now then is there a post processing required over here? No. Post processing? No. So it is a template DFS only. We are just doing DFS, exploring all the neighbors, and at last we get the number of connected components, and n minus the number of connected components will give us the number of removed stones. This is what we are returning.